Somewhere out there, over 1 billion light years from where you are right now, there is a galaxy so large that it makes everything we know look like a speck of dust floating in an endless ocean. A galaxy so massive that if you could somehow travel at the speed of light, the fastest speed possible in the universe, it would still take you millions of years just to cross from one side to the other. This is not science fiction. This is not a guess or a theory. This is real. This is the largest galaxy we have ever found. And tonight, we are going to travel there together. If you enjoy exploring the wonders of the cosmos with us, take a moment to hit that subscribe button and leave a like. It helps us continue bringing you these journeys through the universe. Now, let us begin. When you look up at the night sky on a clear evening, you might see a few thousand stars scattered across the darkness. Each one of those tiny points of light is a sun, many of them far larger and brighter than our own. But here is something that might surprise you. Almost every single star you can see with your naked eyes belongs to just one galaxy. Our galaxy, the Milky Way. The Milky Way is enormous by any human standard. It stretches about 100,000 light years from one edge to the other. To put that in perspective, if you could somehow drive a car at highway speed without ever stopping, it would take you over 1 trillion years to cross our galaxy. That is a number so large that it loses all meaning. 1 trillion years. The universe itself is only about 14 billion years old. And yet, as vast as our galaxy is, it is just one among hundreds of billions of galaxies in the observable universe. Each of those galaxies contains billions or even trillions of stars, each star potentially hosting its own collection of planets. The numbers become so large that our minds simply cannot grasp them. We evolved to understand things like the distance from our cave to the nearest river, or how many berries we might find on a bush. We did not evolve to comprehend the true scale of the cosmos. Our brains are pattern recognition machines, beautifully adapted to the environment of our ancestors. We can intuitively grasp distances we can walk, times we can experience, numbers we can count on our fingers. But when confronted with light years and billions of years and trillions of stars, our intuitions fail us. The numbers become just words, symbols that we can manipulate mathematically, but that we cannot truly feel. This is why astronomers often resort to analogies and comparisons when explaining cosmic scales. They shrink the solar system to the size of a football field, or compress the history of the universe into a single year, or compare galaxies to grains of sand on a beach. These tricks help, a little. They give our limited minds something to grasp, some foothold on the cliff face of cosmic immensity. But ultimately, the universe is too large for any analogy to capture. The true scale of IC 1101, the real extent of Porphyrion's jets, the actual number of stars in the observable universe, these remain beyond human comprehension in any visceral sense. We can know the numbers. We can understand the concepts. But we cannot feel them the way we feel the warmth of sunlight or the weight of a stone in our hand. And perhaps that is okay. Perhaps the inability to truly grasp cosmic scales is part of what makes them so wonderful. They point towards something beyond ordinary human experience, toward a reality that exceeds our evolutionary programming, toward mysteries that will never be fully exhausted no matter how long we study them. But tonight, we are going to try anyway, because out there in the darkness, there are galaxies that dwarf our Milky Way, the same way a mountain dwarfs a grain of sand. There are structures so immense that light itself, traveling at over 600 million miles per hour, takes millions of years to journey across them. And among all the galaxies that astronomers have ever discovered, there are three that stand out as the largest of them all. Three cosmic giants that challenge everything we thought we knew about how big things can get in this universe. The first is called IC 1101. It is a monster of stars, a swirling golden city of light containing an almost unimaginable 100 trillion suns. If our Milky Way is a modest house on a quiet street, then IC 1101 is a castle that stretches beyond the horizon in every direction. The second is named Alcyoneus, after a giant from ancient Greek mythology. Discovered just a few years ago in 2022, this galaxy stunned the scientific community because of the impossible structures that extend from its center. Radio waves shooting out into the void for distances that make even IC 1101 look small. And the third is the newest discovery of all. Found in 2024, it is called Porphyrion, named after the king of the giants in those same ancient myths. This one produces jets of energy that stretch across 23 million light years of empty space. 23 million light years. That is a distance so vast that it touches the very fabric of the cosmic web itself, the largest structure in the entire universe. Tonight, we are going to visit all three of these cosmic giants. We are going to learn how they formed, what they tell us about the nature of the universe, and perhaps most importantly, what they reveal about the ultimate fate of our own galaxy, our own solar system, and our own small world. So settle in, relax, and let your mind drift among the stars. The journey ahead is long, but the wonders we will discover are worth every moment. Close your eyes for a moment. Take a deep breath. Feel the weight of your body against whatever surface supports you. Now imagine that weight is nothing compared to the gravitational pull of 100 trillion suns, all gathered together in one golden sphere of light, 1 billion light years away. Imagine that the breath you just took contains atoms forged in stars that exploded before our solar system even existed. Imagine that the thoughts forming in your mind right now are made possible by cosmic processes that began billions of years ago in the hearts of dying stars. You are a child of the cosmos, as much as any galaxy or star. You are made of the universe, and the universe looks back at itself through your eyes. Tonight, we will use those eyes to gaze upon the largest structures ever found, and in doing so, we will learn something about ourselves. Let us start with a simple question. What exactly is a galaxy? It might seem like a basic thing to ask, but the answer reveals something profound about the universe we live in. A galaxy is, at its heart, a collection of stars held together by gravity. But it is so much more than just stars. Galaxies also contain vast clouds of gas and dust, the raw materials from which new stars are born. They harbor planets, moons, asteroids, and comets beyond counting. And perhaps most mysteriously of all, galaxies are wrapped in enormous halos of something we call dark matter, an invisible substance that we cannot see or touch, but that makes up most of the mass in the universe. Our own Milky Way is what astronomers call a spiral galaxy. If you could somehow travel outside of it and look back, you would see a beautiful pinwheel shape, with graceful arms of stars and glowing nebulae spiraling out from a bright central bulge. Our sun sits in one of those spiral arms, about 2/3 of the way out from the center, in a relatively quiet neighborhood of the galaxy. The Milky Way contains somewhere between 200 billion and 400 billion stars. That number is hard to pin down because many stars are hidden behind clouds of dust or are simply too dim and distant for us to count accurately. But even at the lower estimate, 200 billion is an astonishing number. If you tried to count to 200 billion, saying one number every second without stopping to eat, sleep, or rest, it would take you over 6,000 years to finish. And every single one of those stars is a sun. Many of them are actually larger and more powerful than our own sun. Some are true giants, hundreds of times wider than the star that lights our days. Others are tiny red dwarfs, dim and cool, but burning so slowly that they will shine for trillions of years after our own sun has died. There are blue giants nearing the end of their lives, swelling and pulsating as they prepare for their final explosive deaths. There are stable yellow stars, like our sun, steadily fusing hydrogen in their cores. There are binary systems where two stars orbit each other in an endless gravitational waltz, sometimes close enough to exchange material, sometimes locked in orbits that take thousands of years to complete. There are stellar remnants, white dwarfs and neutron stars and black holes, the corpses of stars that have already lived out their lives. Each star has its own story, its own history, its own collection of planets and moons and asteroids. And the Milky Way contains hundreds of billions of these stories, all unfolding simultaneously, all part of the grand tapestry of our galactic home. This is our home, this immense island of stars drifting through the void. And for most of human history, we thought it was the entire universe. It was not until the 1920s that astronomers finally proved that the fuzzy patches of light visible through telescopes were not clouds of gas within our own galaxy, but entire galaxies in their own right, separated from us by vast gulfs of empty space. This discovery fundamentally changed our understanding of the cosmos. Suddenly, the universe was not just big, it was incomprehensibly, impossibly, mind-breakingly huge. The astronomer Edwin Hubble played a crucial role in this revolution. Using the powerful telescopes at Mount Wilson Observatory in California, he was able to measure the distances to several of those fuzzy patches. What he found was staggering. These objects were not thousands of light years away, as they would be if they were clouds within our own galaxy. They were millions of light years away, far beyond the boundaries of the Milky Way. This meant that each of those fuzzy patches was itself an entire galaxy, comparable in size and complexity to our own Milky Way. The universe was not one island of stars in an infinite void. It was an ocean of islands, stretching out in all directions as far as telescopes could see. Even more remarkably, Hubble discovered that these distant galaxies were moving away from us, and the farther away a galaxy was, the faster it was receding. This led to the realization that the universe itself is expanding, that space is stretching and carrying the galaxies apart like dots on a balloon being inflated. This discovery of cosmic expansion was one of the most profound insights in the history of human thought. It meant that the universe had a beginning, a moment when all of space was compressed into an unimaginably dense and hot state. It meant that the cosmos we see today is a snapshot in time, a stage in an ongoing process of expansion and evolution. It meant that the universe is not static and eternal, as many had assumed, but dynamic and changing. And that brings us back to our three giants, because if the Milky Way, with its hundreds of billions of stars and 100,000 light-year diameter, is just one ordinary galaxy among hundreds of billions, then what does it mean when we find galaxies that are 40 or 50 or even 100 times larger? Let us travel now to the first of our cosmic giants. The journey will take us over 1 billion light-years from Earth, to a place called the Abell 2029 Galaxy Cluster. Galaxy clusters are exactly what they sound like. They are collections of galaxies, sometimes hundreds or even thousands of them, all bound together by gravity into massive cosmic structures. The Abell 2029 cluster sits in the direction of the constellation Virgo, though it is far, far more distant than any of the stars that make up that constellation pattern in our sky. Those stars are mere dozens or hundreds of light years away. The Abell 2029 cluster is over 1 billion light years distant. When you look at light from objects that far away, you are looking back in time. The light that reaches our telescopes from Abell 2029 began its journey over 1 billion years ago, long before complex life appeared on Earth. Dinosaurs would not evolve for another 700 million years after that light was emitted. The earliest humans would not appear for another 999 million years. That light was already ancient when it finally reached our planet. Think about that for a moment. The light you would see through a telescope aimed at Abell 2029 is older than complex multicellular life on Earth. When those photons began their journey across the cosmos, our planet was covered in nothing but single-celled organisms and simple algae. The continents were arranged in configurations unrecognizable to modern eyes. The atmosphere had a different composition. Nothing that we would recognize as an animal existed anywhere on Earth. That light traveled through the void for 1 billion years, crossing distances so vast that they defy comprehension, passing through intergalactic space where atoms are so few and far between that a cubic meter of that space contains only about 1 atom. It traveled while entire star systems were born and died. It traveled while our sun ignited from a cloud of gas and our planets coalesced from the debris. It traveled while life on Earth went through countless evolutionary changes, from single cells to fish, to reptiles to mammals to apes to humans. And finally, after all that time, those ancient photons reached our telescopes, carrying information about a place so far away that light itself, the fastest thing in existence, takes 1 billion years to make the journey. And at the center of this distant galaxy cluster, dominating everything around it like a golden sun surrounded by candle flames, sits IC 1101. This is a galaxy unlike anything else we have ever discovered. While the Milky Way stretches about 100,000 light-years across, IC 1101 spans anywhere from 4 to 6 million light-years from one edge to the other. The uncertainty in that measurement comes from how difficult it is to determine exactly where such a massive galaxy ends and the surrounding space begins. Its outer regions fade gradually into the darkness, blending with the faint light between galaxies. But even at the conservative end of those estimates, IC 1101 is over 40 times wider than the Milky Way. If our galaxy were the size of a dinner plate, IC 1101 would be the size of a small car. To appreciate this scale another way, consider the local group. This is the name astronomers give to the collection of galaxies that includes our Milky Way. The local group contains about 80 galaxies in total, including large spirals like us and Andromeda, smaller spirals like the Triangulum Galaxy, and dozens of dwarf galaxies that orbit the larger ones. The entire local group spans about 10 million light-years across. IC 1101, a single galaxy, is roughly half the size of our entire local group. If IC 1101 were placed where the Milky Way is now, it would engulf not only our galaxy, but also Andromeda, Triangulum, the large and small Magellanic Clouds, and most of the other galaxies in our cosmic neighborhood. We would all be just additional stars in the outer reaches of this golden giant. This is not merely an academic comparison. It reflects the different evolutionary paths that galaxies can take. The Milky Way has remained relatively isolated for much of its history, growing gradually through minor mergers with small satellite galaxies. IC 1101, by contrast, found itself at the center of a dense galaxy cluster surrounded by potential victims with billions of years to consume them all. Try to picture what that means. Our galaxy contains somewhere around 300 billion stars. IC 1101 contains 100 trillion. That is the number 1 followed by 14 zeros. 100 trillion suns, each one a raging nuclear furnace, many of them hosting their own families of planets. The sheer number of worlds that might exist within IC 1101 is beyond calculation. If you could somehow count the stars in IC 1101, 1 star per second, without sleeping or pausing or taking any breaks at all, it would take you over 3 million years to finish counting. 3 million years. Our entire species, Homo sapiens, has only existed for about 300,000 years. You would need to count for 10 times longer than our species has been alive just to enumerate the stars in this single galaxy. And each of those stars is not just a point of light. Each is a world unto itself, a sphere of plasma hundreds of thousands or millions of miles across, churning with nuclear reactions that release more energy every second than all of human civilization has used throughout its entire history. The energy output of IC 1101's 100 trillion stars combined is almost incomprehensible. It is a beacon of light in the cosmos, visible across billions of light years. And those stars are old, very old. While our sun is about 4.5 billion years old, many of the stars in IC 1101 are 11 or 12 billion years old. They were born when the universe itself was young, in a flurry of cosmic creation that has long since ceased. These ancient stars give IC 1101 its distinctive golden yellow color, a warm glow quite different from the blue tinged spiral arms of younger galaxies like our own. You see stars change color as they age. Young stars burn hot and bright, shining with blue-white light. As they grow older and begin to exhaust their fuel, they swell and cool, turning yellow and eventually red. The golden hue of IC 1101 tells us that most of its stars passed through their blue youth billions of years ago. They have settled into a long, slow twilight that will last for ages yet to come. But here is something strange. Despite having 100 trillion stars, IC 1101 is barely forming any new ones. In galaxies like the Milky Way, new stars are born constantly. Clouds of gas collapse under their own gravity, growing denser and hotter until nuclear fusion ignites and a new sun blazes to life. This process has been happening in our galaxy for billions of years and will continue for billions more. IC 1101, by contrast, is what astronomers grimly call red and dead. It has used up most of its gas, the raw material needed to form new stars. Without that gas, no new suns can be born. The galaxy is slowly fading, its existing stars burning out one by one over incomprehensible stretches of time. Eventually, in the far distant future, IC 1101 will grow dark and cold, its last stars sputtering out like candles at the end of a very long night. But that fate lies trillions of years in the future. For now, IC 1101 remains one of the brightest and most massive objects in the entire universe. And at its heart lies something even more extraordinary than the galaxy itself. Imagine falling toward the center of IC 1101. As you travel inward, the stars around you grow more and more densely packed. The golden light intensifies. You pass through layer after layer of ancient suns. each one separated from its neighbors by light years of empty space, yet together forming a blazing river of light that leads ever deeper into the galactic core. And then, at the very center, you would find something invisible, something that emits no light, reflects no radiation, yet dominates everything around it through the sheer power of its gravity. A supermassive black hole. The concept of a black hole is strange enough when you first encounter it, an object so dense that its gravity prevents even light from escaping. A region of space where the normal rules seem to break down, where time and space become so warped that they lose their familiar meaning. Einstein's equations predict black holes, but even Einstein was unsure whether such bizarre objects could actually exist in nature. We now know that they do. Black holes have been detected throughout the universe, from stellar mass black holes a few times heavier than our Sun to the supermassive monsters at the centers of galaxies. And the black hole at the center of IC 1101 is among the most massive ever discovered. Nearly every large galaxy in the universe has a supermassive black hole at its center. Our own Milky Way harbors one called Sagittarius, a star, a dark giant with a mass of about 4 million suns. That sounds enormous, and it is, but the black hole at the center of IC 1101 makes Sagittarius, a star, look like a pebble next to a boulder. The black hole in IC 1101 has a mass estimated between 40 and 100 billion times that of our Sun. 100 billion solar masses, compressed into a single point of infinite density. This is one of the largest black holes ever discovered, approaching what scientists call the upper cosmological limit, the theoretical maximum size that a black hole can achieve. To understand how big this black hole is, consider its event horizon, the boundary beyond which nothing, not even light, can escape. For the black hole at the center of our galaxy, this boundary is about 15 million miles across. That sounds huge, but it would fit comfortably inside the orbit of Mercury. The event horizon of IC 1101's black hole is so large that you could fit our entire solar system inside it multiple times over, from the Sun all the way out past Pluto, dropped into this cosmic drain like a marble down a well. Scientists call black holes of this magnitude ultramassive or even overmassive. That last term hints at a puzzle that still troubles astronomers. IC 1101's black hole seems too big. Based on our understanding of how black holes grow, this one should not exist at the size we observe. Something unusual happened in the history of this galaxy, something that allowed its central black hole to achieve a mass that pushes against the very limits of what physics permits. The answer, we believe, lies in the violent history of IC 1101. This galaxy did not grow to its immense size peacefully. It became a giant through conquest, through a process astronomers call galactic cannibalism. Picture the universe billions of years ago, when it was younger and smaller and more crowded. Galaxies were closer together then, and collisions between them were common. When two galaxies meet, something strange happens. The individual stars almost never actually hit each other because the distances between stars are so vast. Even in the most crowded regions of a galaxy, stars are separated by trillions of miles. Two galaxies can pass right through each other, their stars mixing and mingling like two swarms of fireflies drifting through the same meadow. But while the stars rarely collide, the galaxies as a whole are dramatically transformed. Gravitational forces pull and stretch both galaxies into new shapes. Gas clouds slam into each other at enormous speeds, compressing and heating until they ignite into bursts of new star formation. Tidal forces rip stars away from both galaxies, sending them spinning off into intergalactic space. And the central black holes of both galaxies begin a slow spiral dance toward each other, eventually merging into a single, even larger black hole. IC 1101 has been through this process many times, perhaps 10 times, perhaps 20. Each merger added more stars to its bulk, more mass to its central black hole, more size to its already enormous frame. One merger in particular stands out in the galaxy's history, occurring about 7 billion years ago, when IC 1101 collided with and absorbed another galaxy nearly twice the size of our entire Milky Way. The evidence of these ancient collisions is written in the very structure of IC 1101. Unlike the Milky Way, which has beautiful spiral arms and a well-defined disk, IC 1101 is what astronomers call an elliptical galaxy. It is a vast, roughly spherical swarm of stars, without the organized structure of a spiral. This shape is the typical outcome of major galaxy mergers. The gravitational chaos of multiple collisions destroys any spiral structure that might have once existed, leaving behind a smooth blob of stars moving in random orbits. There is another piece of evidence as well, hidden at the very center of the galaxy. Remember that supermassive black hole we discussed? When astronomers look closely at the core of IC 1101, they find something called a depleted core. This means that the very center of the galaxy, the region immediately surrounding the black hole, has fewer stars than you would expect for a galaxy of this size. The explanation is remarkable. When two supermassive black holes merge, they do not come together quietly. In the final stages of their cosmic dance, they whip around each other at significant fractions of the speed of light. As they spiral inward, they act like a gravitational slingshot, flinging any stars that wander too close out of the galactic core entirely. Over billions of years and multiple mergers, this process has cleared out the center of IC 1101, creating a core region that is surprisingly empty given the galaxy's tremendous mass. Scientists estimate that IC 1101's depleted core represents a stellar mass deficit of nearly 500 billion solar masses. That means nearly 500 billion suns worth of stars have been ejected from the galactic's center over the course of the galaxy's violent history. Those stars are still out there somewhere, drifting through the spaces between galaxies, no longer bound to any cosmic home. This is the story of IC 1101, a galaxy that became a giant by consuming other galaxies, growing larger with each merger, its central black hole swelling to almost unimaginable proportions. It sits now at the center of its galaxy cluster, like a golden emperor on a throne of stars, the largest collection of suns that we have ever found bound together in a single gravitational system. But here is where the story takes an unexpected turn, because in 2022, astronomers announced the discovery of something even larger, something that challenged our very definition of what a galaxy is. Its name is Alcyoneus. The discovery was made by a team of astronomers led by Martin Oy, working at the Leiden Observatory in the Netherlands. They were using data from a remarkable instrument called LOFAR, the Low Frequency Array. LOFAR is not like the telescopes you might picture when you think of astronomy. It does not have a giant mirror or a dome. Instead, it consists of thousands of small radio antennas spread across northern Europe, all working together to detect radio waves from the distant universe. Radio waves are a form of light that our eyes cannot see, but that carries crucial information about some of the most energetic processes in the cosmos. And what LOFAR revealed in the data from a galaxy 3 billion light-years away was almost beyond belief. Alcyoneus is what astronomers call a giant radio galaxy. At its center sits a relatively ordinary-looking elliptical galaxy, similar in some ways to IC 1101, but actually much smaller. If you only looked at the visible light from Alcyonius, you would not think it was anything special. The central galaxy has a diameter of about 240,000 light-years, only about twice the size of the Milky Way. It contains roughly 240 billion times the mass of our Sun, which means it actually has less total mass than our own galaxy. But Alcyonius has a secret. Hidden from view in visible light but blazing brightly in radio waves are two enormous structures called radio lobes, extending outward from the galaxy's center in opposite directions. These lobes are produced by jets of material being shot out from the supermassive black hole at the galaxy's core, jets traveling at nearly the speed of light that eventually slow down and spread out into vast clouds of energetic particles. And the size of these lobes is what made astronomers gasp when they first measured them. Each lobe extends about 5 million light-years from the center of Alcyonius. Together, from the tip of one lobe to the tip of the other, the entire structure spans approximately 16 million light-years. 16 million light-years. Let that number sink in for a moment. To truly appreciate this scale, consider some comparisons. The distance from Earth to the Sun is about 8 light minutes. The distance to the nearest star, Proxima Centauri, is about 4 light-years. The diameter of our entire galaxy is about 100,000 light-years. The distance to the Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years. Alcyonius stretches across 16 million light-years. That is more than 6 times the distance from here to Andromeda. If you place the Milky Way at one end of Alcyonius's radio structure, Andromeda at the other end, and all the space between them filled with empty void, you would still have room for several more Milky Way to Andromeda distances before reaching the far edge. This is not a galaxy in any traditional sense. This is a structure that spans a significant fraction of the space between galaxy clusters. This is something that operates on scales we normally associate with the cosmic web itself. The Milky Way is 100,000 light-years across. Alcyonius, including its radio lobes, is 160 times larger. If our galaxy were the size of a coin, Alcyonius would stretch the length of a tall human being. When news of this discovery broke, some media outlets began calling Alcyonius the largest galaxy ever discovered. But the truth is more complicated and in some ways more interesting than that simple claim suggests. You see, the radio lobes of Alcyonius are not really part of the galaxy itself, at least not in the traditional sense. They do not contain stars. They are not gravitationally bound to the central galaxy in the way that the Milky Way's stars are bound to our galactic center. Instead, they are more like cosmic exhaust, the aftermath of energy being blasted out from the supermassive black hole over millions of years. So whether Alcyonius is truly larger than IC 1101 depends on how you define a galaxy size. If you count only the stars and gravitationally bound matter, IC 1101 is still the champion. But if you consider the total extent of structures created by a single galaxy's central black hole, then Alcyonius reigns supreme. What makes Alcyonius truly puzzling, though, is not its size, but how it achieved that size. Here is the mystery. The central galaxy of Alcyonius is not particularly massive. Its supermassive black hole, while impressive by most standards, contains only about 400 million times the mass of our Sun. That sounds like a lot, but it is actually quite modest for a galaxy producing such enormous radio lobes. For comparison, IC 1101's black hole is over 100 times more massive. The radio power of Alcyonius is also nothing special. It is actually on the lower end of what astronomers observe in other giant radio galaxies. And the rate at which it is producing new stars is almost non-existent, just a tiny fraction of a solar mass per year. So how did such an ordinary galaxy produce such extraordinary structures? The answer may lie in its environment. Alcyonius appears to be located in a filament of what cosmologists call the cosmic web. The cosmic web is the largest structure in the known universe. If you could somehow see all the matter in the cosmos at once, you would notice that galaxies are not distributed randomly. Instead, they are arranged along vast filaments and sheets, like the strands of an impossibly large spider web. These filaments are made primarily of dark matter, the invisible substance that makes up most of the mass in the universe, with galaxies and galaxy clusters forming at the points where filaments intersect. Picture a vast, three-dimensional network stretching across billions of light years in every direction. The strands of this network are made of dark matter and gas, thin rivers of matter flowing through the cosmos. Where these rivers meet, where multiple filaments come together at a single point, matter accumulates and galaxies form. The largest intersections give rise to massive galaxy clusters, cosmic cities containing thousands of galaxies. The spaces between the filaments are vast cosmic voids, regions almost entirely empty of galaxies, stretching for hundreds of millions of light years. This cosmic web is not static. It is constantly evolving, shaped by the competing forces of gravity and dark energy. Gravity pulls matter together, trying to collapse everything into ever denser concentrations. Dark energy pushes space apart, trying to stretch the web until it tears. Klein. The current state of the universe represents a temporary balance between these forces, a moment in cosmic evolution when the web is still intact, but gradually becoming more diffuse. Between the filaments lie enormous voids, regions of space that are almost completely empty of galaxies. Some of these voids are hundreds of millions of light years across, vast deserts of darkness with only the occasional lonely galaxy drifting through. Alcyonius seems to reside in one of the filaments of this cosmic web, in a region where the density of matter is lower than average. The researchers who discovered Alcyonius suggest that this low-density environment may have allowed its radio lobes to expand to such tremendous sizes. With less surrounding matter to slow them down, the jets from the central black hole could travel farther before dissipating. Think of it like blowing a bubble underwater versus blowing one in air. In the denser environment of water, the bubble cannot grow very large before it breaks apart. In less dense air, it can expand to much greater sizes. Similarly, the low-density environment around Alcyonius may have allowed its radio lobes to inflate to record breaking proportions. There is also something poetic about the name Alcyonius. In Greek mythology, Alcyonius was one of the Gigantes, a race of giants born from the earth goddess Gaia and the sky god Uranus. The Gigantes waged war against the Olympian gods in a battle called the Gigantomachy, and Alcyonius was one of the mightiest among them. According to the ancient stories, Alcyonius had a special power. He was immortal as long as he remained in contact with the land where he was born. The hero Heracles, whom the Romans called Hercules, fought against Alcyonius and discovered this secret. Each time he struck the giant down, Alcyonius would rise again, healed by his connection to his homeland. Only when Heracles dragged Alcyonius beyond the borders of his native land could the giant finally be killed. There is something fitting about this name for a galaxy that seems unremarkable until you look beyond its immediate boundaries. The central galaxy of Alcyoneus is nothing special. Just as Alcyoneus the giant appeared mortal like any other when taken from his homeland. But extend your gaze outward, and you discover structures of almost mythical proportions, as if the galaxy's true power lies hidden beyond its visible edges. The naming of astronomical objects after figures from mythology is a long tradition. The planets carry the names of Roman gods. The constellations bear the names of Greek heroes and creatures. Many of the moons of the outer planets are named after figures associated with the corresponding mythological deity. There is something fitting about this practice. Mythology represents humanity's earliest attempts to understand the cosmos, to find meaning and pattern in the movements of the stars. By connecting our scientific discoveries to these ancient stories, we acknowledge the continuity of human wonder, the unbroken thread of curiosity that connects the first astronomers who named the constellations to the scientists who today discovered giant radio galaxies. Alcyoneus and Porphyrion, the mythological giants, challenged the power of the gods themselves. They hurled mountains at the heavens and shook Olympus with their might. They were eventually defeated, but their audacity was legendary. The galaxies that bear their names seem equally audacious, structures so large that they challenge our understanding of what is possible. But the story of cosmic giants does not end with Alcyoneus. Because in 2024, the same team of astronomers announced another discovery. They had found something even larger. Its name is Porphyrion, after the king of the giants in the same Greek myths, and it is the largest structure ever created by a single object in the known universe. Porphyrion was found using the same LOFAR radio telescope system that revealed Alcyoneus. The team was actually searching for something else entirely, trying to map the faint filaments of the cosmic web itself. But in their data, they noticed two faint streaks of radio emission extending from a distant galaxy, streaks so long that they could not possibly be what they appeared to be at first glance. Follow up observations with the giant Metawave radio telescope in India and the W.M. Keck Observatory in Hawaii confirmed the incredible truth. Those streaks were jets of material being blasted out from a supermassive black hole, jets that extend for 23 million light-years from end to end. 23 million light-years. That is 140 times the diameter of the Milky Way. That is larger than the distance between our galaxy and most of our nearest neighbors. That is a size that approaches the scale of the cosmic web itself. To grasp this scale, imagine you could travel at the speed of light. At that impossible speed, you could circle the Earth more than 7 times in a single second. You could reach the Moon in just over a second. You could reach Mars in a few minutes when it is closest to Earth. You could cross the entire solar system in a matter of hours. But to cross the jets of Porphyrion at the speed of light would take you 23 million years. That is longer than humans have existed, longer than most mammal species have existed. You would start your journey when our ancestors were still primitive primates in ancient forests, and you would not arrive until millions of years after every species alive today had either evolved into something unrecognizable or gone extinct. And yet this structure was created by a single object, a supermassive black hole at the center of a distant galaxy, pumping out energy for 1 billion years, sculpting the cosmos on scales that dwarf everything else we have ever observed. Porphyrion is located about 7.5 billion light-years from Earth. When we observe it, we are seeing it as it was when the universe was only about 6 billion years old, less than half its current age. This means that Porphyrion was producing these incredible jets during a very different cosmic era, when galaxies were closer together and the universe was denser and more chaotic. And here is what makes Porphyrion truly extraordinary. Despite producing the largest jets ever observed, the black hole at the center of Porphyrion is not the kind that astronomers expected. For decades, scientists believed that the largest radio jets were produced by a specific type of active black hole, one that is relatively quiet in terms of the radiation it produces, but efficient at converting the material falling into it into powerful jets. These are called jet mode black holes. But Porphyrion's black hole is different. It is what astronomers call a radiative mode black hole, a type that produces a lot of radiation as it devours surrounding matter, but was thought to be incapable of creating jets as large as Porphyrion's. This discovery has forced scientists to reconsider their understanding of how black holes produce jets and how large those jets can grow. The jets of Porphyrion have been active for approximately 1 billion years. For all that time, the central black hole has been steadily pumping out streams of particles and energy, maintaining an almost perfectly straight course across millions of light-years of space. The fact that the jets have remained so stable for so long is itself a mystery. In the turbulent environments of the early universe, you would expect such structures to be disrupted and distorted, but Porphyrion's jets remain remarkably coherent. The power output of these jets is staggering. Combined, they radiate energy equivalent to trillions of suns. As this energy pours out into the surrounding space, it heats the intergalactic medium by about 1 million degrees. This heating may have slowed down the formation of new galaxies in the surrounding region, affecting the evolution of cosmic structures on an enormous scales. There is another implication as well, one that connects these distant cosmic giants to our own existence here on Earth. Scientists believe that the magnetic fields that permeate the cosmos, including the magnetic field that protects our planet from harmful radiation, may have been partially seeded by jets like Porphyrion's. In the early universe, magnetic fields were very weak or non-existent, but over billions of years, as jets from countless supermassive black holes sprayed magnetized plasma across intergalactic space, those magnetic fields gradually built up. The magnetism spread along the filaments of the cosmic web, eventually making its way into forming galaxies, then into forming stars, and finally into forming planets. The magnetic field that shields Earth from deadly solar radiation, that creates the beautiful auroras that dance across our polar skies, that allows compass needles to point north and migrating birds to find their way home. All of this may trace back, in part, to ancient black hole jets like those of Porphyrion. Consider that chain of connection for a moment. Billions of years ago, a supermassive black hole in a distant galaxy began pumping jets of magnetized plasma into intergalactic space. Those jets spread magnetism across millions of light years. Over cosmic time, that magnetism worked its way into the gas that would eventually form new galaxies. That magnetized gas collapsed into stars, some of which exploded as supernovae and enriched the cosmos with heavy elements. Eventually, our sun formed from a cloud of gas and dust, and the planets coalesced from the leftover debris. Earth formed with a molten iron core that, combined with the ambient magnetic field and the planet's rotation, generated our planet's protective magnetic shield. And that magnetic field made Earth habitable. It shields us from the solar wind, a constant stream of charged particles flowing from the sun that would otherwise strip away our atmosphere over time. It protects us from cosmic rays, high-energy particles from distant supernovae that could damage DNA and make the surface uninhabitable. Without Earth's magnetic field, the atmosphere we breathe might have been blown away long ago, and harmful radiation would constantly bombard the surface. We are connected to these cosmic giants in ways we never imagined. The name Porphyrion is fitting for this record-breaking discovery. In Greek mythology, Porphyrion was the king of the Gigantes, the mightiest and most formidable of all the giants. He led the assault against Mount Olympus, attacking both Heracles and the goddess Hera herself. Only the combined power of Zeus's thunderbolts and Heracles' arrows could finally bring him down. Like his mythological namesake, Porphyrion, the galaxy, represents the greatest challenge to our understanding of cosmic scale. Its jets reach out across space like the arms of a giant trying to grasp the heavens themselves. But what do these three galaxies, IC 1101 and Alcyoneus and Porphyrion, tell us about the universe as a whole, and what might they reveal about the future of our own Milky Way? To answer that question, we need to look at the process that created all of these giants, the process of galaxy mergers and galactic evolution that has been shaping the cosmos for billions of years. When the universe was young, only a few 100 million years after the Big Bang, the first galaxies were much smaller than those we see today. They were collections of perhaps a few billion stars at most, drawn together by gravity from the primordial gas that filled the early cosmos. These first galaxies were chaotic and irregular, without the beautiful spiral or elliptical shapes we observe in modern galaxies. The early universe was a violent place. It was denser and hotter than the cosmos we know today. Galaxies were packed closer, together, making collisions more frequent. Black holes at the centers of these young galaxies were actively feeding on surrounding gas, producing intense radiation and powerful jets. The entire cosmos was in a state of cosmic adolescence, energetic and turbulent and constantly changing. Over time, the universe expanded and cooled. Galaxies spread apart, making collisions less common in most regions. The rate of star formation dropped as the available gas was used up or heated too hot to collapse. The jets from supermassive black holes faded as their fuel ran out. The cosmos gradually settled into the quieter state we observe today, but the echoes of that violent youth remain written in the structures we see. The giant elliptical galaxies like IC 1101 bear witness to countless ancient mergers. The jet remnants like those of Alcyoneus and Porphyrion tell stories of black hole activity that has mostly ceased. The cosmic web itself, that vast network of filaments connecting galaxy clusters across billions of light years, preserves the gravitational patterns laid down in the earliest moments of cosmic history. Over time, these small galaxies began to collide and merge. Gravity drew them together, and each merger created a larger galaxy from the combination of the two originals. This process repeated over and over across billions of years, gradually building up the massive galaxies we see today. The process is ongoing. Right now, as you read these words, countless galaxy mergers are happening throughout the universe. Some are violent collisions between roughly equal-sized galaxies, dramatic encounters that will completely transform both participants. Others are more like cosmic muggings, with large galaxies slowly absorbing their smaller neighbors, stripping away stars and gas until nothing recognizable remains. The universe is a violent place on the grandest scales. Galaxies do not drift peacefully through the void, isolated and eternal. They interact, they compete, they consume each other. The largest galaxies achieved their size through conquest, through the gradual accumulation of smaller victims over billions of years. Our own Milky Way has been through this process many times. Evidence of past mergers is written across our galaxy in the form of stellar streams, rivers of stars that do not follow the normal rotational pattern of the galactic disk. These streams are the remnants of smaller galaxies that the Milky Way has consumed over its history. One of the most significant of these past mergers occurred about 10 billion years ago, when the Milky Way collided with a galaxy that astronomers have named Gaia Enceladus. This was a major event, involving a galaxy perhaps 1/4 the mass of the Milky Way at the time. The collision dramatically changed our galaxy's structure, puffing up its disk and contributing many of the stars that now populate our galactic halo. And the mergers continue. Right now, at this very moment, the Milky Way is in the process of consuming several smaller galaxies. The Sagittarius dwarf elliptical galaxy is being stretched and torn apart by our galaxy's gravity, its stars being gradually incorporated into the Milky Way structure. The Canis Major dwarf galaxy may be in a similar state, though astronomers are still debating whether it truly is a separate galaxy or just a part of our own galaxy's warped disk. But the biggest merger of all is still to come. Approximately 2.5 million light-years from Earth, in the direction of the constellation Andromeda, there is another spiral galaxy. It is the farthest object that most people can see with their naked eyes, appearing as a faint smudge of light on very dark, clear nights. This is the Andromeda Galaxy, also known as Messier 31, and it is heading straight toward us. On a clear night far from city lights, you can find Andromeda with your own eyes. Look to the northeast in autumn evenings, and you might spot a small fuzzy patch among the stars. That patch is the combined light of roughly 1 trillion suns, the central bulge of a galaxy much like our own. And every second, that galaxy is getting closer. The light you see from Andromeda tonight left that galaxy about 2.5 million years ago, when our ancestors were just beginning to use stone tools. By the time that light reaches your eyes, it has traveled an almost incomprehensible distance. But compared to the timescales we have discussed tonight, 2.5 million light-years is practically next door. Andromeda is slightly larger than the Milky Way, containing perhaps 1 trillion stars compared to our 300 billion. It is approaching us at a speed of about 110 kilometers per second, roughly 250,000 miles per hour. That sounds incredibly fast, but given the enormous distance involved, the collision will not happen for about 4 to 5 billion years. When it does occur, it will be the most dramatic event in our galaxy's history. But before we explore what will happen, let us appreciate what is happening right now, invisible to our eyes, but measurable with our instruments. Even as you listen to these words, Andromeda is getting closer. Every second, the gap between our two galaxies shrinks by about 100 kilometers. In the time it takes to read this sentence, Andromeda has moved several hundred kilometers closer to us. Of course, that gap is so enormous that even this speed seems like barely any progress at all. 2.5 million light-years is roughly 15 quintillion kilometers. At 100 kilometers per second, it will take an almost unimaginable length of time to close that distance. But the universe is patient. The universe has time to spare. And so, bit by bit, year by year, millennium by millennium, the two largest galaxies in our cosmic neighborhood are drawing together. They have been doing so for billions of years already, since long before life on Earth crawled out of the oceans. They will continue doing so for billions of years more, until finally they meet in a collision that will reshape both galaxies entirely. Computer simulations show what will happen in great detail. As Andromeda approaches, it will grow larger and larger in our sky over millions of years. Eventually, it will no longer appear as a faint smudge, but as a prominent feature stretching across the heavens, a second river of stars to rival our own Milky Way. Then the collision will begin in earnest. The outer regions of both galaxies will start to interact, gravitational forces pulling streams of stars out of both galaxies into long tidal tails. The two galaxies will pass through each other, their stars, intermingling but almost never actually colliding with each other because of the vast distances between individual stars. During this first passage, both galaxies will be dramatically distorted. The Milky Way's beautiful spiral arms will be stretched and warped. Andromeda's disk will be similarly deformed. Stars that were once following orderly orbits around their galactic centers will be flung onto new trajectories, some heading toward the other galaxy, some being thrown outward into intergalactic space. The gas in both galaxies will behave differently from the stars. While stars can pass through each other without colliding, gas cannot. When the vast clouds of gas in both galaxies meet, they will collide and compress. This compression will trigger an enormous burst of star formation, lighting up both galaxies with millions of new suns being born simultaneously. For a brief cosmic moment, measured in millions of years, the merging galaxies will blaze with the light of their stellar baby boom. After this first passage, the galaxies will swing back around for a second encounter, then a third. With each passage, they will become more and more entangled, their original spiral structures becoming increasingly disrupted. Eventually, after perhaps 2 billion years of cosmic dance, the two galaxies will fully merge into a single massive elliptical galaxy. Astronomers have already given this future galaxy a name. They call it Milkomeda, a combination of Milky Way and Andromeda. And when the merger is complete, Milkomeda may look something like a smaller version of IC 1101, a giant elliptical galaxy with hundreds of billions or even trillions of stars, its graceful spiral arms replaced by a smooth golden glow. What will happen to our solar system during this cosmic collision? The good news is that the stars in both galaxies are so far apart that the chance of our Sun actually colliding with another star is essentially zero. If you think of stars as grains of sand, then even in the densest parts of a galaxy, those grains are separated by miles. Two galaxies can pass right through each other without any of their stars ever coming close to touching. However, the gravitational forces of the merger could dramatically affect our solar system's orbit. Simulations suggest that there is a significant chance, perhaps 1 in 8, that our Sun could be flung out of the merged galaxy entirely, cast out into intergalactic space to drift among the voids between galaxies. Even if we stay within the merged galaxy, our position would likely change dramatically. Currently, our Sun orbits about 26,000 light-years from the center of the Milky Way. After the merger, we might find ourselves much farther out, perhaps 3 times our current distance from the galactic center. The night sky would look completely different, filled with unfamiliar constellations, as the stars around us would be entirely different from those we see today. But here is something important to remember. By the time this collision occurs, Earth will already be uninhabitable. Our Sun is gradually getting brighter as it ages. In about 500 million to 1 billion years, this increasing brightness will cause Earth's oceans to boil away, ending all life on our planet's surface. By the time Andromeda collides with the Milky Way, Earth will have been a lifeless, Venus-like world for billions of years. If humanity still exists by then, we will have long since moved on. Perhaps Perhaps we will have spread to other planets, other star systems, other galaxies. Perhaps we will have found ways to survive that we cannot even imagine today. Or perhaps we will have gone extinct. Our brief flicker of consciousness long since vanished from a universe that continues on without us. The cosmos does not care about our plans or our hopes. The galaxies will merge whether we are here to witness it or not. IC 1101 will continue its slow fade into darkness. Alcyoneus will spread its invisible wings ever wider across the void, and Porphyrion's jets will continue their billion-year journey through intergalactic space. These are processes that operate on timescales so vast that they make human history look like the blink of an eye. Our entire civilization, from the first cave paintings to whatever future wonders we might achieve, occupies a mere instant compared to the eons required for galaxies to form and merge and evolve. And yet, there is something remarkable about our position in this cosmic drama. We are the universe becoming aware of itself. Through our telescopes and our mathematics and our curiosity, we have learned to see the cosmos as it truly is. We have discovered IC 1101 and Alcyoneus and Porphyrion. We have mapped the cosmic web and predicted the merger of our own galaxy with Andromeda. For a brief moment in the history of the universe, matter has organized itself into beings capable of understanding where it came from and where it is going. Whatever else we might be, we are that, and that perhaps is wonder enough. Let us return now to the beginning, to that summer night in 1790 when a German-born musician named William Herschel pointed his homemade telescope at a tiny patch of sky in the direction of the constellation Virgo. Herschel was not born to be an astronomer. He spent most of his early life as a musician, playing the oboe in military bands, and later becoming an organist and music teacher in the English city of Bath. Music was his passion and his profession, and he was quite good at it, composing symphonies and concertos that were performed throughout England. But Herschel had an insatiable curiosity about the natural world, and in his spare time he began reading books about mathematics and optics. This led him to astronomy, and astronomy led him to a frustration that would change his life. The telescopes available for purchase were simply not powerful enough to see the things he wanted to see. So Herschel did what came naturally to him. He decided to build his own telescopes. He taught himself the incredibly difficult art of grinding and polishing mirrors, spending countless hours in his workshop shaping discs of metal into the precise curves needed to focus light. His sister Caroline assisted him in this work, and together they produced telescopes more powerful than any that existed at the time. The work was exhausting and sometimes dangerous. On one occasion, a furnace exploded while Herschel was casting a metal mirror, sending molten metal across the floor. But he persisted, driven by an obsession to see deeper into the cosmos than anyone had seen before. 9 years before that summer night, Herschel had made a discovery that shocked the world. Using one of his telescopes, he noticed a small object that moved against the background of fixed stars. At first, he thought it might be a comet, but careful observations revealed something far more significant. Herschel had discovered a new planet, the first to be found since ancient times. We now call it Uranus. This discovery made Herschel famous. The King of England appointed him as the royal astronomer and provided funds for him to build ever larger and more powerful telescopes. Herschel dedicated the rest of his life to mapping the heavens, cataloguing thousands of stars, nebulae, and other celestial objects. On June 19, 1790, Herschel's telescope pointed toward a faint smudge of light in the constellation Virgo. He carefully recorded its position and noted its appearance. Like many similar objects he had observed, it appeared to be a fuzzy patch rather than a point of light like a star. Herschel had no way of knowing what he was looking at. At the time, astronomers believed that objects like this were clouds of gas within our own Milky Way, perhaps regions where new stars were forming. It would be more than a century before astronomers realized the truth. That fuzzy patch was not a cloud of gas at all. It was an entire galaxy containing hundreds of billions of stars, located over 1 billion light-years away. Today, we call it IC 1101, after its entry number in the index catalogue of nebulae and star clusters compiled in the late 19th and early 20th centuries. Herschel could never have imagined what he was seeing. The very concept of a galaxy beyond our own did not exist in his time. He died in 1822, more than 100 years before Edwin Hubble proved that the universe extended far beyond the boundaries of the Milky Way. But Herschel's observation was recorded, and that record allowed later astronomers to find IC 1101 again and study it with ever more powerful instruments. Today, we can see it in detail that would have seemed like magic to Herschel. We can measure its size and estimate its mass and detect the radio emissions from its central black hole. We can even determine what kinds of stars it contains and how old they are. This is the power of science. Each generation builds on the work of those who came before. Herschel's observations, made with a hand-built telescope in an age of candlelight and horse-drawn carriages, contributed to a chain of discovery that would eventually reveal the true nature of the cosmos. Caroline Herschel, William's sister, deserves special mention. She was his constant companion in astronomy, assisting with observations, recording data, and performing calculations. She discovered several comets in her own right and became the first woman to be officially recognized for scientific work in England. The Herschels worked together for decades, mapping the heavens and cataloguing thousands of objects that astronomers would study for centuries to come. Their work continued after William's death in 1822. His son, John Herschel, became a distinguished astronomer in his own right, extending his father's catalogues and making important observations from the southern hemisphere. The Herschel family's contributions to astronomy span multiple generations, a dynasty of discovery that helped transform our understanding of the universe. When William Herschel observed that faint smudge in Virgo in 1790, he had no idea he was looking at the largest collection of stars in the observable universe. He recorded it simply as another nebulous object among the thousands he catalogued. It would take more than 2 centuries for astronomers to fully appreciate what he had found, and that chain continues today. Right now, astronomers around the world are making observations that will not be fully understood for decades or centuries. Somewhere in the data being collected tonight, there may be clues to discoveries we cannot yet imagine. Perhaps there are galaxies even larger than IC 1101 waiting to be found. Perhaps there are structures beyond Porphyrion's jets, stretching across scales we have not yet learned to measure. The universe keeps revealing new wonders, no matter how much we learn. Every time astronomers think they have catalogued all the types of objects that exist, something new appears. Every time physicists believe they understand the fundamental laws, an anomaly arises that demands explanation. The universe seems inexhaustible, an endless source of mysteries waiting to be uncovered. This should not surprise us. The cosmos has been around for nearly 14 billion years. It contains more atoms than there are grains of sand on all the beaches of Earth. It encompasses distances so vast that light itself, the fastest thing in existence, takes billions of years to cross them. How could such a vast and ancient realm not contain surprises? The history of astronomy is a history of surprises. Early astronomers thought the Earth was the center of everything, only to discover that we orbit the Sun. They thought the Sun was special, only to learn that it is one ordinary star among hundreds of billions in our galaxy. They thought our galaxy was the entire universe, only to find that it is one of hundreds of billions of galaxies. At every turn, the universe has proven to be larger, more complex, and more wonderful than anyone imagined. The discoveries of IC 1101 and Alcyonius and Porphyrion are just the latest chapters in this ongoing story. They will not be the last. Somewhere in the cosmos, there are objects we have not yet found, phenomena we have not yet understood, wonders we have not yet imagined. The adventure of discovery continues. Consider what we now know about the 3 galaxies we have explored tonight. IC 1101 taught us that galaxies can grow to almost unimaginable sizes through the process of galactic cannibalism. Its 100 trillion stars and its colossal supermassive black hole show us the ultimate fate of matter in the densest regions of the cosmos. Everything nearby has been consumed, drawn into a single golden giant that dominates its entire galaxy cluster. Alcyonius showed us that size is not just about how many stars a galaxy contains. The structures that a galaxy can create, the influence it can have on its surroundings, can extend far beyond its gravitational boundaries. Those 16 million light-year radio lobes produced by a relatively ordinary galaxy remind us that the universe is full of surprises. Even a modest black hole in the right environment can shape space on scales that dwarf the largest stellar assemblies. And Porphyrion demonstrated that the impact of a single object can reach to the scale of the cosmic web itself. Those 3 million light-year jets may have heated intergalactic space, influenced the formation of other galaxies, and seeded the magnetic fields that eventually made life possible on worlds like Earth. The cosmos is not a collection of isolated objects, but a vast interconnected web, where events in one corner can have consequences across billions of light years. These 3 giants also teach us something about our own place in the universe. Our galaxy is not special. It is one of hundreds of billions, and not particularly large or unusual by cosmic standards. The processes that shaped IC 1101 and Alcyonius and Porphyrion are the same processes that shape the Milky Way. We are part of the same cosmic story, playing out across incomprehensible distances and timescales. This realization can be either terrifying or liberating, depending on how you choose to see it. For some, the vastness of the cosmos makes human existence seem meaningless, a brief flicker of awareness in an indifferent void. For others, that same vastness makes human existence seem miraculous, a rare and precious phenomenon in a universe mostly filled with empty space and mindless matter. Both perspectives have merit. The universe is indeed vast and mostly empty, and governed by physical laws that do not care about human hopes or fears. But the universe has also produced us, beings capable of appreciating that vastness, of measuring those empty spaces, of understanding those physical laws. In a cosmos of countless galaxies, we are the ones asking questions. That is not nothing. That may, in fact, be everything. The Milky Way will not always look the way it does today. It is changing, evolving, consuming smaller galaxies, and eventually merging with Andromeda. Billions of years from now, our current home may be unrecognizable, transformed into something like a smaller version of the giants we have explored tonight. And perhaps that is the most profound lesson of all. Nothing in the universe is permanent. Stars are born and die, galaxies collide and merge. Even the largest structures we know of are temporary arrangements of matter and energy, destined to change over billions and trillions of years. This impermanence extends to everything we know. The continents on Earth are slowly drifting, rearranging themselves over millions of years. The sun is slowly brightening, making Earth gradually warmer until it becomes uninhabitable. The universe itself is expanding, carrying galaxies apart from each other at ever-increasing speeds. On human timescales, these changes are imperceptible. The continents seem fixed. The sun seems constant. The stars seem eternal. But on cosmic timescales, everything is in motion. Everything is changing. Everything is evolving towards some future state that will be as different from the present as the present is from the distant past. There is something both terrifying and beautiful about this cosmic impermanence. Terrifying because nothing we create or accomplish will last forever. Beautiful because change makes existence interesting, makes evolution possible, makes the universe a dynamic and creative place rather than a static and boring one. The stars we see tonight are not the same stars our distant ancestors saw. Some of those ancient stars have died, exploding as supernovae or fading into white dwarfs. Other stars have been born, igniting from clouds of gas and beginning their long journeys toward death. The constellations our ancestors named have slowly changed, their shapes as the stars moved against each other. In another 100,000 years they will be unrecognizable. We exist in a brief window of cosmic time when the universe is old enough to have formed complex structures like galaxies and planets and life, but young enough that those structures have not yet faded away. The stars still shine, the galaxies still swirl, and on at least one small planet orbiting one ordinary star in one unremarkable galaxy, beings have evolved who can look up at the night sky and wonder. That wonder is precious. It connects us to Herschel and to every other human who has ever gazed at the stars and asked what they are. It connects us to whatever future minds might exist, organic or artificial, who will continue to explore the cosmos long after we are gone. And in some sense, it connects us to the universe itself, to the vast processes of cosmic evolution that made us possible. We are stardust that has learned to contemplate the stars. So the next time you have a chance to look up at a truly dark night sky, take a moment to consider what you are seeing. Those points of light are suns, each one a raging nuclear furnace like our own, but separated from us by distances that would take lifetimes to cross even at the speed of light. Beyond them, invisible to the naked eye but revealed through telescopes, are billions of galaxies, each containing billions of stars, stretching out in all directions to the very edges of the observable universe. The light you see from those stars has been traveling for years, sometimes hundreds or thousands of years. When you look at the bright star Sirius, you are seeing light that left that star about 8 years ago. When you look at Polaris, the North Star, you are seeing light from about 400 years ago, from around the time of Shakespeare. When you look at the Andromeda Galaxy with binoculars or your naked eyes, you are seeing light from over 2 million years ago, from a time before modern humans existed. Every glance at the night sky is a glance into the past. The stars you see are not the stars as they are now, but the stars as they were when their light began its journey toward your eyes. Some of the stars you can see may no longer even exist. They may have exploded as supernovae centuries or millennia ago, but the light from those explosions has not yet reached us. We are looking at ghosts, at echoes, at the frozen past preserved in photons. This is one of the strangest and most wonderful aspects of astronomy. We cannot see the present. We can only see the past. And the farther we look in distance, the farther back in time we see. When astronomers observe IC 1101, they are seeing the galaxy as it was over 1 billion years ago. The galaxy that exists now, at this very moment, is different from what we observe. But we will never see that present moment version. By the time its light reaches us, another 1 billion years will have passed. And somewhere out there, over 1 billion light years away, the golden glow of IC 1101 continues its long, slow fade toward darkness. Alcyonius continues to spread its invisible wings across 16 million light-years of void. Porphyrion continues to blast its jets across the cosmic web, heating space and spreading magnetism to the farthest reaches of the intergalactic medium. These are our neighbors in the cosmos. These are the other great cities of stars that share our universe. We will never visit them, never see them with our own eyes, never touch their ancient light directly. But we can know them. Through our science and our curiosity, we have reached across the void and learned their secrets. That is something wonderful. That is something worth celebrating. And now, as we come to the end of our journey tonight, I want to leave you with one final thought. The universe does not owe us meaning. It does not owe us a purpose or significance. In the face of scales like those we have explored tonight, 100 trillion stars in IC 1101, 23 million light-year jets from Porphyrion, billions of years of cosmic evolution, it would be easy to feel small and insignificant. But consider this. The universe has existed for nearly 14 billion years. For most of that time, there was no one to appreciate its wonders. Stars were born and died unobserved. Galaxies collided and merged with no witness to their cosmic dance. The universe was simply happening, with no mind to recognize its beauty or comprehend its vastness. Then, on a small rocky planet orbiting an unremarkable star in an ordinary galaxy, something remarkable occurred. Matter organized itself into patterns complex enough to become aware, to look up at the sky and wonder, to build telescopes and make discoveries and feel awe. We are that awareness. For a brief moment in cosmic history, the universe has found a way to know itself. Through our eyes, through our minds, the cosmos beholds its own wonders. IC 1101 and Alcyonius and Porphyrion existed for billions of years before any creature on Earth knew they were there. But now we know. Now their light has meaning, because there is someone to receive it, to measure it, to understand what it tells us about the nature of reality. Think about what that means. For most of the universe's history, there was no meaning anywhere. There were atoms and energy and physical processes, but no mind to contemplate them, no consciousness to ask why they existed or what they signified. The galaxies swirled through the void in perfect silence, their beauty going unappreciated because there was no one to appreciate it. Then, in what amounts to the blink of an eye on cosmic timescales, intelligence emerged, first on Earth, and perhaps on countless other worlds throughout the cosmos. Suddenly, the universe had observers. Suddenly, there were beings who could look up at the stars and feel awe. Suddenly, the physical processes that had been occurring for billions of years had witnesses. We are those witnesses. We are the universe experiencing itself, contemplating itself, trying to understand itself. Every question we ask about the cosmos is the cosmos asking questions about itself through us. Every discovery we make is the universe discovering its own nature. This is not a burden. It is a gift, and it is a responsibility to keep looking, to keep wondering, to keep pushing the boundaries of what we know, generation after generation, building an ever clearer picture of the cosmos we call home. The largest galaxy we have ever found is out there, 1 billion light years away, and we are here, on our small blue world, looking back at it with wonder. That connection across all that space and time is something magical, something worth pondering as you drift off to sleep tonight, dreaming of distant stars and ancient light and the endless wonders that await us in the cosmos. Thank you for joining us on this journey. Until next time, keep looking up, keep wondering, and remember that you are part of something vast and beautiful and endlessly fascinating. The universe is waiting to be explored. But before we say goodnight, let us linger a little longer in the cosmos. There is still so much more to explore, so many more wonders to contemplate. Let us go deeper into the nature of these galactic giants. Let us understand not just what they are, but what they mean for our understanding of everything. The tools we use to study these cosmic giants are marvels of human engineering. Radio telescopes like LOFAR, which discovered Alcyonius and Porphyrion, work differently from the optical telescopes most people imagine when they think of astronomy. Instead of collecting visible light through mirrors and lenses, radio telescopes detect electromagnetic radiation at much longer wavelengths. Radiation that is invisible to our eyes, but carries crucial information about the most energetic processes in the universe. The LOFAR array consists of thousands of small antennas spread across Europe, from Sweden in the north to Bulgaria in the south, all working together as a single enormous instrument. By combining signals from all these antennas, astronomers can create images of the radio sky with incredible detail. This technique, called interferometry, allows scientists to study objects that would be impossible to resolve with any single telescope. When astronomers first began measuring the sizes of galaxies in the early 20th century, they assumed that galaxies came in a relatively narrow range of sizes. Surely, they thought, there must be some physical limit to how large a galaxy can grow. Gravity can only pull so much matter together before something stops the process. The universe is expanding after all, carrying galaxies away from each other. How could any single galaxy become truly enormous? IC 1101 challenged those assumptions in ways that took decades to fully appreciate. The galaxy was first recognized as unusually large in the 1960s, when improved telescopes and techniques allowed astronomers to estimate distances to faint objects more accurately. As the true distance to IC 1101 became clear, so did its true size. This was not just a large galaxy. This was something unprecedented. But measuring the size of IC 1101 turned out to be surprisingly difficult. The galaxy does not have sharp edges like a planet or a star. Instead, its brightness fades gradually as you move outward from the center. At some point, the galaxy becomes so faint that it blends into the background glow of the night sky, and astronomers have to make judgment calls about where the galaxy ends and empty space begins. Different measurement techniques have yielded different results. Some estimates put IC 1101 at about 4 million light-years across. Others suggest it might extend to 6 million light-years or even more. The uncertainty reflects the genuine difficulty of measuring something so vast and so distant. What we do know is that IC 1101 sits at the very top of the galactic size distribution. Out of the hundreds of billions of galaxies in the observable universe, IC 1101 is among the largest handful ever discovered. It represents an extreme of galactic evolution, a worst-case scenario for any smaller galaxy unfortunate enough to wander too close to its gravitational influence. The galaxy's location helps explain its enormous size. IC 1101 sits at the exact center of the Abell 2029 galaxy cluster, in what astronomers call the bottom of the potential well. This means that IC 1101 occupies the point of lowest gravitational potential in the cluster, the place where everything else tends to fall toward. Over billions of years, smaller galaxies in the cluster have slowly spiraled inward, pulled by the collective gravity of the cluster toward its center. And when they reached that center, they encountered IC 1101 waiting for them. One by one, those smaller galaxies were absorbed, their stars becoming part of IC 1101's growing bulk, their black holes merging with the monster at the galaxy's heart. This process is called brightest cluster galaxy formation, or BCG formation for short. Nearly every large galaxy cluster has a BCG at its center, a dominant galaxy that has grown large by consuming its neighbors. IC 1101 is simply an extreme example of this process, a BCG that has had billions of years and abundant material to become truly colossal. The Abell 2029 cluster itself is impressive. It spans 5 to 8 million light-years across, comparable in size to IC 1101 itself. The cluster contains hundreds of smaller galaxies, though many of those have already been partially stripped of their stars by IC 1101's gravity. Hot gas fills the space between galaxies, heated to millions of degrees by gravitational compression and radiating strongly in X-rays. In fact, X-ray observations of the Abell 2029 cluster have provided crucial information about IC 1101's true mass. By measuring how hot the cluster gas is and how it is distributed, astronomers can calculate the total gravitational pull holding everything together. Those calculations suggest that IC 1101 and its surrounding dark matter halo contain mass equivalent to several trillion suns. Dark matter deserves special attention here. Although we call IC 1101 a galaxy of 100 trillion stars, those stars represent only a small fraction of its total mass. The majority of the galaxy's mass is made up of dark matter, an invisible substance that interacts with ordinary matter only through gravity. Dark matter forms a vast halo surrounding IC 1101, extending even farther than the visible galaxy. This halo is the gravitational scaffold that holds everything together, that attracted smaller galaxies over billions of years, that provided the framework within which IC 1101 grew to its present size. We do not know what dark matter actually is. Despite decades of searching, no one has ever directly detected a dark matter particle. We know it exists because we can see its gravitational effects, but its true nature remains one of the biggest mysteries in modern physics. Physicists have proposed many possible explanations. Perhaps dark matter consists of a new type of subatomic particle that barely interacts with ordinary matter. Perhaps it is made of primordial black holes formed in the early universe. Perhaps it is something even more exotic, something our current theories have not yet imagined. Experiments around the world are searching for evidence that might distinguish between these possibilities. But so far, the nature of dark matter remains unknown. What we do know is that without dark matter, galaxies like IC 1101 could not exist. The visible stars alone do not have enough gravitational pull to hold a galaxy together, especially one spinning as fast as observations suggest. The dark matter provides the extra gravity needed to keep the stars bound together, preventing the galaxy from flying apart. In IC 1101, the dark matter halo is truly enormous, extending far beyond the visible edge of the galaxy. Some estimates suggest that the total extent of IC 1101's dark matter halo might reach 10 million light-years or more, making it one of the largest gravitationally bound structures in the universe. This raises an interesting philosophical question. What do we mean when we say IC 1101 is 4 to 6 million light-years across? If we count only the stars, that range might be accurate. But if we count the dark matter halo, the galaxy might be much larger. And if we count the extended envelope of faint intracluster light, stars that have been stripped from other galaxies and now orbit within the cluster, but are gravitationally associated with IC 1101, the number gets larger still. Galaxies are not simple objects with clear boundaries. They are complex systems embedded in larger structures, connected to their environments by webs of gravity and matter and history. IC 1101 is the most extreme example of this complexity. A galaxy so large that it begins to merge with its cluster, its individual identity becoming blurred at the edges. The supermassive black hole at the center of IC 1101 tells its own remarkable story. Black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. If the star is massive enough, nothing can stop the collapse, and all the matter gets compressed into an infinitely small point of infinite density called a singularity. Around this singularity, space becomes so warped that nothing can escape, not even light. The boundary of this region is the event horizon, the point of no return. Supermassive black holes like the one in IC 1101 did not form from single collapsing stars. They grew over billions of years, feeding on gas and dust and even other black holes. Each time IC 1101 absorbed another galaxy, it also absorbed that galaxy's central black hole. The two black holes would orbit each other, gradually spiraling together until they merged in a catastrophic event that released enormous amounts of energy as gravitational waves. This process, repeated many times over billions of years, built up the massive black hole we observe today. Each merger added more mass to the black hole and, as we discussed earlier, flung stars out of the galactic core through gravitational slingshot effects. The result is a black hole so large that it challenges our understanding of physics. At somewhere between 40 and 100 billion solar masses, IC 1101's black hole is approaching theoretical limits on how large a black hole can grow. Beyond a certain mass, the Eddington limit suggests that radiation pressure from infalling matter should prevent the black hole from growing any further. Yet here is a black hole that seems to have exceeded, or at least approached those limits. Some physicists have proposed that the black hole might have formed through unusual processes in the early universe, giving it a head start that allowed it to reach its current size. Others suggest that the limits might not apply as strictly as once thought, that black holes in certain environments might be able to grow larger than theory predicts. The true answer remains unknown. What we can observe is the influence this black hole has on its surroundings. The inner regions of IC 1101 show that characteristic depleted core, the absence of stars that were flung away by black hole mergers long ago. The core radius is about 14,000 light-years, 10 times larger than the cores of other giant elliptical galaxies. This is the gravitational scar left by billions of years of violent evolution. Despite its enormous mass, IC 1101's black hole is surprisingly quiet. Most supermassive black holes produce intense radiation as matter falls into them, creating what astronomers call an active galactic nucleus. But IC 1101's black hole is relatively dormant, producing only faint radio emissions. It has essentially run out of nearby material to consume. This is another consequence of the galaxy's age and evolution. All the gas that once filled IC 1101 has either been formed into stars or heated to such high temperatures that it can no longer collapse. Without fresh fuel, the black hole has nothing to eat. It sits at the center of its galaxy, impossibly massive but strangely silent, a sleeping giant waiting for more matter to wander within its grasp. Now let us return to Alcyonius and explore its mysteries in greater depth. The discovery of Alcyonius in 2022 represented a triumph of modern astronomical techniques. The LOFAR telescope system that found it is fundamentally different from traditional optical telescopes. Instead of collecting visible light through mirrors and lenses, LOFAR detects radio waves using thousands of small antennas spread across thousands of square kilometers. Radio waves have much longer wavelengths than visible light, which means they can pass through clouds of dust that would block optical observations. They also reveal physical processes that produce little or no visible light, like the relativistic jets from supermassive black holes that create giant radiolobes. The team that discovered Alcyonius was not specifically looking for giant radio galaxies. They were surveying the northern sky as part of the LOFAR 2-meter sky survey, creating a catalogue of radio sources for future study. In the process, they discovered over 8,000 new giant radio galaxies, objects with radio structures exceeding about 3 million light-years in size. Alcyonius stood out immediately. Its radiolobes were so large that at first the astronomers suspected they might be two separate objects, not connected to a single galaxy at all. Only careful analysis confirmed that both lobes trace back to the same central source, making Alcyonius the largest radio galaxy ever discovered at that time. To understand why Alcyonius's size is so surprising, we need to understand how radio galaxies work. At the center of every radio galaxy is an active, supermassive black hole. As matter falls toward the black hole, it forms a swirling disk of superheated gas called an accretion disk. Magnetic fields in this disk become twisted and amplified, eventually channeling some of the infalling matter into jets that shoot out perpendicular to the disk at nearly the speed of light. These jets are among the most powerful phenomena in the universe. They carry enormous amounts of energy outward from the black hole, plowing through the gas surrounding the galaxy and eventually slowing down as they encounter resistance. When the jets finally slow down enough, they spread out into the large diffuse structures we call radiolobes. The size of the radiolobes depends on several factors. More powerful jets can push farther into their surroundings before losing momentum. Lower density environments offer less resistance, allowing jets to travel farther. And older sources have had more time for their lobes to expand. What makes Alcyonius puzzling is that none of these factors seem sufficient to explain its enormous size. The central galaxy of Alcyonius is not particularly massive, with a stellar mass of about 240 billion solar masses and a black hole of about 400 million solar masses. It is actually on the lower end of what astronomers observe for giant radio galaxies. There is no obvious source of extra power that would allow its jets to travel so far. The radioluminosity of Alcyonius is also unremarkable. It produces radio waves at a rate similar to, or even lower than, many smaller radio galaxies. Whatever is making Alcyonius so large, it is not simply that it has an unusually powerful engine. The age of the source might contribute. Radiolobes expand over time as the jets continue to pump energy into them. An older source has had more time to grow. But estimating the age of a radio galaxy is difficult. and there is no clear evidence that Alcyonius is significantly older than other giant radio galaxies. That leaves the environment as the most likely explanation. Alcyonius appears to reside in a region of lower than average cosmic density, a filament of the cosmic web where the intergalactic medium is particularly thin. With less material to slow them down, the jets from Alcyonius's black hole could travel much farther than they would in a denser environment. This hypothesis is supported by measurements of the pressure inside Alcyonius's radiolobes. The internal pressure of a radiolobe tells us how much it is pushing outward against its surroundings. Alcyonius's lobes have some of the lowest pressures ever measured in a radio galaxy, about 5 times 10 to the -16th pascals. This extremely low pressure suggests that there is very little external resistance pushing back against the lobes, consistent with a low-density environment. If this interpretation is correct, Alcyonius teaches us something important about cosmic structure. The size that a radio galaxy can achieve is not just about the properties of the galaxy itself. It is also about where that galaxy happens to be located. In the right environment, even a relatively ordinary galaxy can produce extraordinary structures. The implications extend beyond Alcyonius itself. If low-density environments allow radiolobes to grow larger, then we should expect the largest radio galaxies to be found in the emptiest regions of space. This makes them valuable probes of cosmic structure, markers of the voids and thin filaments that make up the cosmic web. Alcyonius is also interesting because of what it might tell us about the warm-hot intergalactic medium, often abbreviated as WEM. This is the gas that fills the filaments of the cosmic web, heated to temperatures between about 100,000 and 10 million degrees Kelvin. The WEM is extremely difficult to observe directly because it is so diffuse and emits light at wavelengths that are easily absorbed. But the radio lobes of giant galaxies like Alcyonius interact with the UWIM as they expand. By studying how the lobes behave, astronomers can learn about the properties of the gas they are pushing into. Alcyonius, with its enormous lobes and low internal pressure, is particularly sensitive to the properties of its surroundings, making it an ideal natural laboratory for studying the intergalactic medium. The research team that discovered Alcyonius noted that their finding raises as many questions as it answers. Why do some galaxies produce giant radio lobes, while others do not? What determines whether a radio galaxy will become a giant? Are there even larger radio galaxies waiting to be discovered, perhaps in even emptier regions of space? The answer to that last question came just 2 years later, with the discovery of Porphyrion. Porphyrion represents a new frontier in our understanding of how black holes can influence their cosmic surroundings. Its jets extend 23 million light-years from end to end, making it about 40% larger than Alcyonius. But the differences between the two galaxies go far beyond mere size. While Alcyonius's black hole is in what astronomers call jet mode, relatively quiet in terms of radiation but efficient at producing jets, Porphyrion's black hole is in radiative mode, producing significant amounts of radiation as it consumes surrounding matter. Before Porphyrion's discovery, astronomers believed that radiative mode black holes could not produce jets as large and powerful as jet mode black holes. Porphyrion proved that assumption wrong. This has significant implications for our understanding of black hole physics. It suggests that the processes governing jet formation are more complex than we thought, that jets can achieve extreme sizes under conditions we did not expect. The detailed mechanisms remain unclear, but Porphyrion has opened new avenues for research. The age of Porphyrion's jets adds another dimension to the mystery. Based on their size and the speed at which they must have grown, astronomers estimate that the jets have been active for about 1 billion years. For all that time, the black hole has been steadily pumping out streams of particles and energy, maintaining a remarkably consistent power output and direction. This stability is itself remarkable. Black holes are fed by accretion disks that can be chaotic and variable. The material feeding the black hole comes from its surroundings, which change over time as the galaxy moves through space and interacts with other objects. Yet Porphyrion's jets have remained pointed in the same direction, with the same power, for 1 billion years. Whatever is controlling the jets must be remarkably stable. The implications for the cosmic environment are profound. Porphyrion's jets are pumping about 10 to the 39 watts of power into intergalactic space. That is equivalent to the energy output of trillions of suns, being deposited not into a galaxy, but into the near-empty void between galaxies. This energy has heated the intergalactic medium in Porphyrion's vicinity by about 1 million degrees. Such heating could have significant effects on the formation of galaxies in the surrounding region. Galaxies form when gas cools and condenses under gravity. If that gas has been preheated by jets like Porphyrion's, it may not be able to cool efficiently, slowing or even preventing galaxy formation. In other words, Porphyrion may have influenced the cosmic landscape on scales of tens of millions of light years, preventing galaxies from forming in its vicinity, shaping the distribution of matter in ways that will persist for billions of years to come. A single object, through the power of its jets, has left a permanent mark on the structure of the universe. The discovery of Porphyrion also suggests that such giant jets were more common in the early universe than in the present day. Porphyrion dates from a time when the universe was about half its current age, when galaxies were closer together and the cosmic web was denser. Its black hole is in radiative mode, which was the dominant mode of black hole activity in the young universe. If radiative mode black holes can produce jets as large as Porphyrion's, then the early universe may have been crisscrossed by enormous jet systems, heating and magnetizing intergalactic space on vast scales. This could explain several puzzling observations, including why the intergalactic medium is so hot and why magnetic fields seem to be present throughout the cosmos. The magnetic fields are particularly interesting from the perspective of life in the universe. Magnetic fields play crucial roles in many astronomical processes, from the formation of stars and planets to the protection of planetary atmospheres from harmful radiation. Earth's magnetic field shields us from the solar wind and from cosmic rays, making the surface habitable for life. Where did Earth's magnetic field come from? Ultimately, it comes from the rotation of molten iron in our planet's core. But that iron had to come from somewhere. It was forged in the hearts of massive stars and scattered into space when those stars exploded as supernovae. Those explosions happened in our galaxy, which inherited its magnetic field from the gas out of which it formed. And that gas may have been magnetized in part by ancient jets like Porphyrion's, spreading magnetism through the cosmos billions of years before our sun was born. This chain of connection, from black hole jets to intergalactic magnetism, to galactic magnetic fields, to planetary magnetic fields, to the protection of life, is one of the most remarkable discoveries of modern astronomy. It suggests that we are connected to the largest structures in the universe in ways we never imagined. So what do these three galaxies, IC 1101 and Alcyonius and Porphyrion, tell us about the future? What fate awaits our own Milky Way, and by extension, our own solar system and planet? We have already discussed the coming merger with Andromeda, the collision that will transform our galaxy into something unrecognizable over the next several billion years. But let us consider this future in more detail. The Andromeda Galaxy is currently about 2.5 million light-years away. It is approaching us at about 110 kilometers per second. At that rate, it will take about 4 to 5 billion years for the two galaxies to actually collide. But recent research has complicated this picture. A study published in 2025 incorporated new data from the Gaia spacecraft, which has measured the positions and motions of billions of stars with unprecedented precision. This study found that when the gravitational influences of other nearby galaxies are included, particularly the Large Magellanic Cloud and the Triangulum Galaxy, the outcome becomes less certain. The revised calculations suggest that there is only about a 50% chance of a direct collision between the Milky Way and Andromeda. The other 50% of scenarios involve close encounters that do not result in immediate merger, though gravity would eventually pull the two galaxies together regardless. If and when the merger happens, the process will unfold over billions of years. The first close passage will dramatically distort both galaxies, pulling out long streams of stars called tidal tails. Intense bursts of star formation will occur as gas clouds in both galaxies are compressed by the collision. The night sky, viewed from Earth or any planet that still exists, would be transformed into something spectacular, filled with the combined light of two colliding galaxies. After the first passage, the two galaxies will swing apart, carried by their mutual momentum, before gravity pulls them back together again. This process of approach and separation will repeat several times, with each passage removing more energy from the system until the galaxies can no longer escape each other. The final merger will produce a giant elliptical galaxy that astronomers have nicknamed Milkomeda. This new galaxy will contain the combined stars of both the Milky Way and Andromeda, roughly 1.5 trillion stars in total. Its beautiful spiral arms will be gone, replaced by a smooth elliptical shape similar to IC 1101, but much smaller. The supermassive black holes at the centers of both galaxies will eventually merge as well. This process will take additional time after the stellar merger is complete, as the two black holes slowly spiral together through a process called dynamical friction. When they finally merge, the event will release enormous amounts of energy as gravitational waves, ripples in the fabric of space-time that will spread outward across the cosmos. What about our solar system? Computer simulations suggest that there is a good chance our Sun will be flung into a new orbit, farther from the center of the merged galaxy than its current position. There is also a small but non-zero chance, about 12%, that the solar system will be ejected from the galaxy entirely, cast out into intergalactic space to drift forever between the stars. But as we noted earlier, this is all academic from the perspective of life on Earth. Long before any of this happens, our planet will have become uninhabitable. The Sun is gradually brightening as it ages, and within about 500 million to 1 billion years, Earth's surface will become too hot for liquid water. By the time Andromeda collides with the Milky Way, Earth will have been a dead world for billions of years. If humanity or our descendants still exist by then, we will have moved on to other worlds, other stars, perhaps other galaxies. The Milky Way-Andromeda merger would be an event to observe from a safe distance, a cosmic spectacle to be appreciated rather than feared. Beyond the Andromeda merger, the very long-term future of galaxies is equally interesting. As the universe continues to expand, driven by the mysterious force we call dark energy, galaxies are moving apart from each other. This expansion is accelerating, which means that the distances between galaxies are growing faster and faster over time. Eventually, in the very distant future, most galaxies will have moved so far apart that light from one will never be able to reach another. The observable universe, which currently contains hundreds of billions of galaxies, will shrink to contain only our local group, the small cluster of galaxies gravitationally bound to the Milky Way and Andromeda. Over even longer timescales, the stars themselves will burn out. The most massive stars have already lived and died many times over since the universe began. Smaller stars burn their fuel more slowly and can last for trillions of years. The smallest red dwarf stars, which make up the majority of stars in the universe, will continue to shine for tens of trillions of years, far longer than the current age of the cosmos. But eventually, even the smallest stars will exhaust their fuel and fade away. The universe will enter what physicists call the degenerate era, a time when the only stellar objects remaining are white dwarfs, neutron stars, and black holes. These remnants will slowly cool over inconceivable stretches of time, releasing their remaining heat into an ever-expanding, ever-emptying cosmos. In the extremely far future, even these remnants will decay. White dwarfs and neutron stars are held together by quantum mechanical forces that seem permanent on human timescales. But theory suggests that over periods of time measured in years with exponents of exponents, even these forces will eventually be overcome. Protons may decay, causing ordinary matter to slowly dissolve into radiation. Black holes will evaporate through a process called Hawking radiation, shrinking over unimaginable eons until they finally wink out of existence. This far future is almost impossible to contemplate. The timescales involved dwarf even the current age of the universe by factors beyond human comprehension. The universe, as it exists today, filled with stars and galaxies and the possibility of life, is just the opening act of a cosmic drama that will play out over timescales we cannot truly imagine. In the final stages, even the black holes will be gone. The universe will consist of nothing but radiation, slowly cooling and spreading ever thinner as space continues to expand. The temperature will approach absolute zero. The density will approach zero. Nothing will ever happen again. This is sometimes called the heat death of the universe. It is the final victory of entropy, the thermodynamic tendency toward disorder and equilibrium. All the complexity and beauty that the universe has created, the galaxies and stars and planets and life, will have been erased, leaving behind only a vast, cold, empty darkness. The ultimate fate of the universe, according to current physics, is a state of maximum entropy, a cold, dark, empty expanse in which nothing ever happens again. This is sometimes called the heat death of the universe, but we should be careful about extrapolating physics into such distant futures. Our current understanding is incomplete. Dark energy, which is driving the accelerating expansion, is not fully understood. There may be physical processes or phenomena that we have not yet discovered that could change these predictions. And in any case, these timescales are so vast that they have no practical relevance to human concerns. The heat death of the universe, if it happens at all, lies trillions upon trillions of years in the future. The universe we know, filled with galaxies and stars and planets and the possibility of life, will persist for aeons yet to come. Let us bring our attention back to the present, to the wonders that exist right now, waiting to be discovered. The three galaxies we have explored tonight, IC 1101 and Alcyonius and Porphyrion, represent the extremes of what galaxies can become. They push against the boundaries of size and power and influence, showing us just how magnificent the cosmos can be. But they are not alone. The universe contains hundreds of billions of galaxies, each one unique, each one with its own history and structure and collection of stars. Some are tiny dwarf galaxies with only a few million stars. Others are massive spirals like our own Milky Way. Still others are peculiar galaxies distorted by collisions or interactions, their shapes warped into rings and bridges and tidal tails. Every galaxy is a world unto itself, a vast collection of stars and planets that could harbor untold wonders. The Milky Way alone is estimated to contain billions of planets, many of them potentially capable of supporting life. If similar proportions hold for other galaxies, then the number of worlds in the observable universe is beyond calculation. We have no idea how many of those worlds might harbor life. We have no evidence yet of life beyond Earth, but the sheer numbers suggest that we are unlikely to be alone. Somewhere out there, on some planet orbiting some star in some galaxy, there may be other beings looking up at their own night sky, wondering about their own place in the cosmos. Perhaps some of those beings live in IC 1101, on a planet orbiting one of those 100 trillion ancient stars. If so, their night sky would look very different from ours. Instead of the band of the Milky Way stretching across the heavens, they would see a uniform glow of golden light, the combined radiance of countless elderly suns. The constellations they might identify would be formations of globular clusters, dense balls of stars that orbit within the galaxy's halo. Or perhaps life exists in Alcyoneus, on some world near the galaxy's center. Such beings might never know that their galaxy produces enormous radio lobes extending millions of light years into space. Radio waves are invisible after all, and the lobes are far beyond the range of any plausible observation. They might think their galaxy was just another ordinary elliptical, never suspecting the hidden wings that stretch across the cosmos. These are speculations, of course. We have no way of knowing whether life exists in any of these galaxies. But the possibility is there, written in the vast numbers and the laws of chemistry and physics that seem to favor complexity wherever conditions permit. The search for life beyond Earth is one of the great scientific endeavors of our time. Telescopes are being built that will be able to analyze the atmospheres of planets around other stars, looking for chemical signatures that might indicate biological activity. Missions are being planned to explore the potentially habitable moons of Jupiter and Saturn, where liquid water may exist beneath icy surfaces. Radio telescopes scan the sky for signals that might indicate intelligent civilizations elsewhere in the galaxy. The James Webb Space Telescope, launched in 2021, is already revolutionizing our understanding of planetary atmospheres. It can detect the chemical composition of gases surrounding planets orbiting distant stars, potentially identifying molecules like oxygen, methane, or water vapor that might indicate the presence of life. In the coming years and decades, even more powerful telescopes will push these capabilities further. Meanwhile, robotic explorers continue to study the worlds of our own solar system. Mars rovers search for evidence of ancient microbial life on a planet that may have been habitable billions of years ago. Spacecraft are planned to visit Europa and Enceladus, icy moons that harbor subsurface oceans where life might exist in the darkness beneath miles of frozen crust. Even Titan, Saturn's largest moon with its lakes of liquid methane, is a target for exploration, its alien chemistry potentially hosting forms of life we have never imagined. The odds are difficult to calculate. We know that life emerged on Earth fairly quickly once conditions became suitable, which suggests that life may form easily given the right circumstances. We know that the basic building blocks of life, amino acids and nucleotides and other organic molecules, form readily in many environments throughout the cosmos. We know that liquid water, often considered essential for life as we know it, exists in many places beyond Earth. But we also know that we have no evidence yet of life anywhere else. Despite decades of searching, we have not found any signals from alien civilizations, any fossils of Martian microbes, any chemical signatures in planetary atmospheres that unambiguously point to biological activity. The universe seems to be full of the ingredients for life, yet life itself, as far as we can currently tell, exists only here. So far, we have found nothing, but the search has barely begun. The universe is vast, and our technology is still primitive compared to what will someday be possible. The absence of evidence is not evidence of absence, and even if we never find other life, even if we turn out to be alone in this enormous cosmos, that would be a discovery of profound significance. It would mean that life, and especially intelligent life, is incomprehensibly rare, a precious phenomenon that emerged once and only once in all of cosmic history. The responsibility to preserve and spread that life would become even more pressing. We do not know which of these possibilities is true. But either way, the universe we have explored tonight is magnificent beyond words. IC 1101, with its 100 trillion stars, Alcyonius with its 16 million light-year wings, Porphyrion with its jets that reach to the scale of the cosmic web itself. These are wonders that exist whether or not anyone is there to observe them. There is something humbling about contemplating objects this large. Our daily concerns, our hopes and fears and ambitions seem impossibly small against the backdrop of IC 1101's 100 trillion ancient suns. The arguments we have, the worries that keep us up at night, the achievements we strive for, all of these seem to shrink to insignificance when we remember that there are jets of plasma stretching across 23 million light-years of empty space. And yet, that sense of insignificance is not the whole story. Because we are the ones who discovered these wonders. We are the ones who built the telescopes and did the mathematics and pieced together the story of cosmic evolution. The universe may be vast and indifferent, but we are not. We care, we wonder, we seek to understand. In a cosmos of mindless physical processes, of atoms bouncing according to the laws of physics, something remarkable has happened. Matter has organized itself into patterns complex enough to ask questions about its own origins. We are the universe becoming aware of itself, and that awareness is precious beyond measure. But someone is there to observe them. We are. And that makes all the difference. Through our telescopes and our mathematics and our never-ending curiosity, we have reached out across the void and touched these distant giants. We have measured their sizes and estimated their masses and puzzled over their mysteries. We have connected them to the story of cosmic evolution, understanding how they formed from the primordial gas of the early universe and how they will continue to evolve over billions of years to come. This is the gift of science. It allows us to see beyond the limits of our senses, to understand things that no human eye will ever directly witness. The largest galaxy we have ever found is 1 billion light-years away, far beyond any possible journey. But through science, we can know it. We can appreciate its majesty. We can understand our connection to it through the shared physics that governs all of space and time. As you drift off to sleep tonight, perhaps dreaming of distant stars and ancient light, remember that you are part of this story. Your atoms were forged in stars that lived and died billions of years ago. The carbon in your cells, The oxygen you breathe, the iron in your blood, all of it was cooked in stellar furnaces and scattered across space in supernova explosions. You are literally made of star stuff, as the poet said. The calcium in your bones was forged in the cores of massive stars that exploded billions of years ago. The iron in your blood came from supernova explosions that briefly outshone entire galaxies. The oxygen you breathe was created through nuclear fusion in stellar interiors. Every element in your body heavier than hydrogen and helium, and that is most of them, was cooked in a cosmic furnace and scattered across space in a stellar death. You are a walking collection of atoms that were once inside stars. You are recycled cosmic material, organized into a pattern complex, enough to think about its own origins. When you look up at the night sky, you are looking at the factories that made you, the forges that created the very atoms you are using to contemplate them, and the stars that made you were themselves part of galaxies, collections of billions of suns held together by gravity and dark matter, evolving over cosmic time through mergers and interactions. The galaxy that gave birth to our sun was itself shaped by its environment, by the cosmic web of dark matter that guided its formation, by the jets and radiation from ancient black holes that magnetized the primordial gas. We are connected to IC 1101 and Alcyonius and Porphyrion, not just through observation, but through physics, through the shared laws of nature that govern everything from the smallest atom to the largest galaxy. We are all made of the same fundamental particles, obeying the same fundamental forces, following the same fundamental principles. This is perhaps the deepest insight that astronomy offers. We are not separate from the universe. We are part of it. We emerge from it. We depend on it. And someday we will return to it, our atoms recycled into new stars and new planets, and perhaps new life. The largest galaxy we have ever found is not so different from the smallest, in the end. Both are collections of matter and energy, organized by gravity into patterns that evolve over time. Both contain the same elements, the same forces, the same physics. The difference is only one of scale, and scale, as we have seen tonight, is relative. Our galaxy seems large to us because we are small. IC 1101 seems enormous because it contains 100 trillion stars. But to the universe as a whole, even IC 1101 is just another galaxy, one of hundreds of billions, a single point of light in a cosmos that stretches for billions of light years in every direction. What matters is not size, but awareness. The universe existed for billions of years before any mind arose to appreciate it. Stars burned, galaxies collided, black holes devoured matter, all without witness. But now there are witnesses. Now there are beings who can look up at the night sky and feel wonder. That wonder is precious. It connects us to our ancestors who painted animals on cave walls by firelight and told stories about the points of light in the sky. It connects us to the astronomers of the past who painstakingly mapped the heavens with instruments we would now consider primitive. And it connects us to whatever beings might exist elsewhere in the cosmos, looking up at their own skies and asking their own questions about the nature of reality. Wonder is the beginning of wisdom, an ancient philosopher once said. The capacity to be amazed, to feel awe, to recognize that the universe contains things beyond our understanding. This is one of the most precious gifts of conscious existence. Without wonder, we would take the cosmos for granted, treating the stars as mere points of light, rather than the nuclear furnaces they truly are. IC 1101 inspires wonder through sheer scale. 100 trillion stars gathered together over billions of years of galactic cannibalism, forming a golden city of light, that dominates its entire corner of the cosmos. To contemplate IC 1101 is to feel the vertigo of vastness, the dizzying realization that the universe operates on scales far beyond anything we encounter in daily life. Alcyonius inspires wonder through mystery. How does a relatively ordinary galaxy produce radio lobes spanning 16 million light-years? What peculiar combination of circumstances allowed this one object to grow so much larger than its peers? The questions it raises are as compelling as the answers we have found so far. Porphyrion inspires wonder through connection. Its jets have touched the cosmic web itself, spreading energy and magnetism across distances that span significant fractions of the observable universe. And through that spreading, through the magnetic fields it helped seed, Porphyrion may have contributed to the conditions that made life possible on the worlds like Earth. We are linked to this distant giant in ways that still astonish even the scientists who study it. We are all part of the same cosmic story, the story of matter organizing itself into ever more complex patterns, the story of energy flowing from hot to cold, from concentrated to diffuse, creating pockets of order and meaning along the way. The story of the universe coming to know itself through the minds that have emerged within it. IC 1101 and Alcyonius and Porphyrion are chapters in that story. They show us what is possible, what the laws of physics permit, what extremes matter and energy can achieve. They humble us with their vastness and inspire us with their beauty. And now, truly, it is time to rest. The galaxies will continue their slow dance through the cosmos while you sleep. IC 1101 will continue its long fade toward darkness, its ancient stars burning ever more dimly as the eons pass. Alcyonius will continue to stretch its invisible wings across the void, its radio lobes expanding ever so slowly into emptier and emptier space. Porphyrion will continue to pump energy into the cosmic web, heating and magnetizing the intergalactic medium with the inexhaustible patience of a process that operates over billions of years. And tomorrow, when you wake, the universe will still be there. The stars will still be shining. The galaxies will still be spinning. The cosmic web will still be stretching across the void, connecting everything to everything else in a vast network of gravity and matter and light. You will go about your day, dealing with the concerns and joys and struggles of human existence. But somewhere in the back of your mind, perhaps you will remember tonight. Perhaps you will remember that there are galaxies containing 100 trillion stars, black holes weighing billions of suns, jets of energy stretching across millions of light years. Perhaps you will remember that you are part of something vast and ancient and ongoing. And perhaps, when you next have a chance to look up at a clear night sky, you will see it with new eyes, not just as a scattering of points of light, but as a window into the cosmos. Each of those points is a sun. Each sun may host planets. Each planet is a world with its own story. And beyond those stars, invisible to the naked eye but revealed through telescopes, are billions of galaxies stretching out to the very edges of the observable universe. We are small, but we can comprehend the large. We are brief, but we can imagine the eternal. We are limited to a single planet, but we can explore the cosmos with our minds. This is the human condition, to be finite beings in an infinite universe, yet capable of grasping, if only partially, the nature of that infinity. To be mortal creatures, contemplating immortal processes. To be bound by time and space, yet able to reach across billions of light years and billions of years to touch the largest structures in existence. The largest galaxy we have ever found is out there right now, doing whatever galaxies do when no one is watching. slowly evolving, slowly fading, slowly becoming something else over timescales that make human history look like the blink of an eye. Its 100 trillion stars continue their ancient orbits, circling a central black hole so massive that it defies easy comprehension. Some of those stars are dying right now, swelling into red giants or collapsing into white dwarfs or exploding in supernovae that briefly outshine the entire galaxy. Other stars, though rare in IC 1101's aged population, may still be forming in isolated pockets of gas, new suns, igniting in a galaxy that has mostly given up on creating new light. The radio lobes of Alcyoneus continue their slow expansion, pushing ever outward into the emptiness of intergalactic space. The electrons and protons that make up those lobes are spiraling through magnetic fields, emitting the radio waves that first revealed the galaxy's existence to astronomers on distant Earth. Those particles will continue their slow dance for millions of years yet, gradually losing energy, gradually fading, until eventually they disperse entirely into the void. Porphyrion's jets continue their relentless journey across the cosmos. The supermassive black hole at the center of that distant galaxy is still pumping energy outward, still maintaining its billion-year vigil of creation and destruction. The jets will continue heating and magnetizing the intergalactic medium, spreading their influence across ever greater volumes of space until eventually something causes them to falter, to sputter, to finally go dark. All of this is happening right now as you listen to these words. The universe does not pause while we contemplate it. The galaxies do not wait for our attention. The processes that shape the cosmos continue regardless of whether any mind is present to observe them. And we are here, on our small blue world, knowing about it, understanding it, appreciating it. That is enough. That is more than enough. That is everything. Thank you for joining us on this journey through the cosmos. May your dreams tonight be filled with distant stars and ancient light and the endless wonders of the universe that is our home. Sleep well. And when you wake, remember that you live in a cosmos of unimaginable beauty and scale, a cosmos that has produced galaxies containing 100 trillion suns, jets stretching across 23 million light years, and at least one small planet where matter has learned to contemplate itself. The night sky that awaits you when you next look up is not just a decoration. It is a window into infinity. Every star you see is a sun, burning with nuclear fire, potentially hosting worlds where other forms of life might gaze back at our direction and wonder if anyone is looking their way. Every dark space between those stars contains untold numbers of galaxies too faint for our eyes to see. Each galaxy a vast collection of suns and worlds and possibilities. We live in an age of cosmic awareness that would have seemed like magic to our ancestors. We can measure distances to galaxies, billions of light years away. We can detect the faint whisper of radio waves emitted by electrons spiraling through magnetic fields across intergalactic space. We can trace the history of the universe back to within moments of its birth. We can predict, with reasonable confidence, what will happen to our galaxy billions of years in the future. This knowledge is a treasure beyond price. It has come to us through centuries of patient observation, through the work of countless scientists building on each other's discoveries, through technologies that allow us to see what no human eye alone could ever perceive. We are the inheritors of a tradition of inquiry that stretches back to the first humans, who looked up at the stars and wondered. Carry that tradition forward. Keep looking, keep wondering, keep asking questions about the nature of reality and your place within it. The cosmos rewards curiosity with wonders beyond imagination. That planet is Earth. Those beings are us, and the cosmos awaits. There is a quietude that comes with contemplating such vast scales. The worries of everyday life, the concerns that occupy our thoughts, seem to shrink when placed against the backdrop of IC 1101's 100 trillion suns. The arguments we have, the deadlines we stress about, the frustrations we feel, all of these become whispers against the silence of intergalactic space. This is not to say that our daily lives do not matter. They matter enormously to us and to the people around us. But there is comfort in knowing that we are part of something so much larger. Comfort in knowing that the universe has been here for 14 billion years and will continue for trillions more. Comfort in knowing that whatever happens in our brief individual lives, the cosmic story will go on. The stars will continue to shine. The galaxies will continue to evolve. And perhaps, somewhere in the vastness of space and time, other minds will arise who will contemplate these same wonders, who will ask these same questions, who will feel this same awe. We are not alone in the sense that we are part of a cosmic process, a universal story that encompasses everything that exists. Even if no other intelligent beings exist in the entire observable universe, we are connected to the cosmos through the atoms in our bodies, the energy that powers our thoughts, the laws of physics that allow us to exist at all. The largest galaxy we have ever found is out there, 1 billion light years away, and we know about it. We have measured it. We have tried to understand it. That act of knowing, of reaching across inconceivable distances with our minds and our instruments, is itself a kind of miracle. Let that profound miracle be your companion as you drift peacefully off to sleep tonight. Let the knowledge of IC 1101 and Alcyoneus and Porphyrion settle into your dreams like ancient starlight finally arriving home. Let the vastness of the cosmos wrap around you like a warm blanket of stars. Good night.